Good morning. How you doing, folks? Today we're going to be covering, we're going to be starting Chapter 6, and in which case we're going to be covering Sections 6.1 and 6.2. Today, just for reference, today we are on schedule. Today is Monday the 8th. So 6.1 and 6.2, right on target. Yay us. The packet that I have prepared for you, well, that will be available in Canvas, looks like this. It's a summary of the information that we're discussing. I have found that, this is very old, incidentally, people often confuse these two, and since they are different, they will use the wrong set of rules. So, in a nutshell, I made this diagram, and I'm going to draw it again, basically, to discuss the differences, right, and the similarities, compare and contrast, all right, so that you know which set of rules to follow when tasked with simplifying or evaluating expressions versus solving equations, right? A lot of times a kid will come up to you and say, when you say you want me to simplify this, do you mean you want me to solve it? And, you know, colloquially, in regular speak, you would go, yeah, all right, but you should clearly tell them, well, you should reserve this word for this particular thing because it's a different set of rules, really, okay? You'll see what I mean in a bit. There's a lot of terminology, so I made this diagram. It has a word bank, right? And I'll go through this with you, right? I'm going to basically have it projected onto this board, and then I'll fill in the diagram with you. And if you're not content with my explanation, I swiped this from the textbook, which describes both of these tasks. And lastly, well, not lastly, this is a scaffolding that I basically employ whenever I'm solving equations. Now, you might have been taught to do it a certain way, and I would not try to dissuade you from using anything that is comfortable, familiar, and works, right? But I will show you some practical examples of this, right? And then there are 2 pages of word problems that I typed up so that I can again project them. All right, so do try to print those, and we'll go through them. Actually, what I wanted to show you first is a very short history lesson, because since we're in Chapter 6, and incidentally, I'm getting ahead of myself here, if you are so inclined, a good way to organize is to fold over a little triangle like this, all right, so that you know where you're starting from. All right. I would teach the kids that, especially if you're teaching the kids in 3rd grade or maybe even younger. All right. Get them in the habit of being organized. Right. That's the whole point of the thing I'm about to show you. All right. You have to teach them how to be organized. They don't have that skill. At least most children don't come to school with that ability. So you give them that. All right. Set an example. Anyhow, this is going to be a little silly, all right, because I'm working on an old drafting table here that I kind of slapped together. And it was my father's, actually, and I just added to it. And I'm using a T-square here. It's for sheetrock, all right, to draw some lines. All right, now you won't have to do this. You have a notebook, hopefully, but I thought I would basically illustrate, literally, all right, where we are in the history of math, right? The conversation, right? Because it gives a person, you know, more of an identity to tell them, okay, here you are, and here's where the stuff that came before you, all right? Rather than just say, you know, vomit math on them, you know, math. All right, here's some stuff for you. All right. Anyhow, let's get organized. So, taking my own advice here, I'm going to try to simulate some lines. It's nice and straight, and we'll talk about this. Hopefully, I left myself a sufficient amount of space in all cases. All right. Maybe, maybe not. We'll see. All right. maybe as a heading here, because again, I'm no historian, but so I'm not really sure if my labeling is correct, but let's get some approximate dates here, frames, shall we say, a frame of time, a time frame, if you like, and then we'll put some periods in here, and subjects, and then some concepts. And, or maybe a better word is revolution. A revolution in thought. You know? Again, you don't have to do this, and if you want to, you can skip right over it, but I think anybody who's a human, anyone who's alive, would want to know, you know, where this stuff comes from and how that relates to all of us. See if this goes across enough. Is that right? So I'm just going to make a little heading here, like so. Now again, I'm not a historian, but I did look up some rough estimate of time. So you could perhaps with greater precision, you know, and labeling, change this at will. Recorded history starts about 5000 BCE. So let's call this before 5000 BCE, before the Common Era. This is a brand new mark and it's already fading. Right. An appropriate name for a period like that, I would assume, is prehistory. Right, that makes sense, right? Because it's before recorded history. The subject, now humans existed before recorded history. It's just, you know, in quite a long time as far as we can tell. But they didn't write anything down, right? Nonetheless, the concept of counting, this is nice and dark. No, it's fucking me already. The concept of counting, it must have existed, right? Even before there were symbols, right? That were written onto, you know, some form of paper or tablet. So here's a period, prehistory, and here's a subject in terms of math, right? Counting, right? Even animals, you know, have some sort of number sense. That's really the concept that I'm really getting at. That is to say, animals that don't speak. Right? We are animals that speak, right? Here you go. Math animal, right? We are, right? Anyhow, if you were to, there was an experiment I remember reading about one time where they had, you know, just to see if animals do in fact have a number sense, an idea of that there's more or less, even if they're not very precise, right? They may not go, you know, stand up on their hind legs and give a speech, right? But anyhow, if you took 2 plates of food, an obviously large amount of food and an obviously small amount of food, and then let the animal decide, you know, what to eat from, they will naturally gravitate towards the larger amount, because even though they can't go, oh, there's 500 acorns on this plate here, all right, they know more than less than, right? At least in some instances, right? So this is the concept, this is the revolution in thought, you know, a number sense, right? So if you're counting, even if it's with your fingers, right, even if it's with, you know, rocks or something, you know, or some other, like knots even, which is more sophisticated, all right? This is prehistoric, we'll say, right? I don't know for sure, all right, but it probably, my estimate is that, okay? You're not getting tested on this, I'm just giving you some frame of reference, right, literally. Okay? That's the first idea upon which math is based, right? This may end up being silly, but I'm going to keep trying to draw ruling lines here. All right, now recorded history approximately 5,000. Begins about 5,000 BCE. And again, I'm being very general. Let's say it goes from 5,000 to about 500 CE, or you might say AD. I myself was raised Catholic, all right? So AD is Anno Domini, Latin for in the year of our Lord. But to be broad-minded, all right, common era is perfectly sufficient, and it means the same thing. All right, so BCE is not just before Christ. All right, it's before the common era. All right, it is the same frame, basically. Anyhow, the if we're going to call this a frame of time, that's not just numbers. Let's just refer to this as vaguely the ancient. All right, and the concept that was around, or was sort of, shall we say, state of the art, you know, for such a very long time was arithmetic. I like this. Gotta get rid of that green. The green's never right. Arithmetic. If you start with a number sense, with the ability to count, right? Even again, if it's with your fingers or with rocks or something else that's not written. The next logical step, the next evolution, revolution in thought, right, is to perform some operation upon the numbers, right? What is adding really, but is slightly more sophisticated form of counting, right? And we were looking at the ancient Egyptian hieroglyphics, right? They had symbols at this point to represent quantities. Right? But what did they do to just represent larger and larger quantities? They kept drawing the same picture over and over again. That's adding, all right? Not in the most sophisticated way, granted, but it works. So, what is arithmetic? Right? It's having actual numeral symbols and things that you do to the symbols, operations. Which is adding, subtracting, multiplying, and dividing ultimately. Right. Remember, it may not have been apparent, at least even to our ancestry, right, immediately, but these are opposite concepts, right? These are opposite concepts, and I would go one step further and say this, right? Counting is the foundational concept of math. Adding is a slightly more sophisticated form of counting. It's counting with symbols rather than your fingers, right? Multiplying is a slightly more sophisticated form of adding. It's adding efficiently, right? All right, moving on. Also in the ancient, but I would have to guess a little bit after that point, that arithmetic became prevalent, is the concept of geometry. Geometry as a subject is quite old. Right? There's geometry, though, that is the oldest form of geometry, which is, maybe a different color maybe to emphasize. Blue or red would be better. Such limited colors here. There's Egyptian geometry. Right. And then there's Greek geometry. Now, Egyptian geometry, just again to give you a vague idea of time, Egypt as sort of the locus of Western thought was, let's just say 3,000. This I'm going to put an asterisk here because again I'm estimating 3,000 BCE to maybe 300, you know, something like that. And I like nice round numbers in case you hadn't noticed. Right. Whereas the Greece as a locus of Western civilization, right, is after the Egyptians naturally. So let's just, again, estimating Greek civilization, say something like 1200 BCE to 146. My sister is working inside. My sister works for a credit union, and unfortunately she's talking to people on a headset, and they're deaf. But I can hear her, and so can you. For all time preserved. Anyhow, I apologize, but this is Corona world where we share space. Right? I'm gonna stop and wait a moment.
G as in George. G as in George. L. G, R.
Where was I? Here. Okay. Counting, arithmetic, geometry comes after these two. All right. But there's Egyptian geometry first. Right. And in terms of a revolution in thought, well, geometry is naturally about shapes.
Oh, I must have got her old extension number.
And measurements of some sort.
Roxanne's old extension number.
All right, and one might call these practical applications.
Okay, thank you so much.
Whereas Greek geometry, which is, again, is borrowing from the locus of activity that existed before you or concurrently, would be referred to as logical geometry. Now, if you've ever taken geometry in high school, you probably have some inkling as to what that is. The bane of high school students' existence, sophomores especially, is geometric proofs around times. Anyhow, logic, that is what you might call deductive reasoning.
Okay, thank you. I'll be on the lookout. Aw, thanks. Aw, well, we're happy to have you. Thank you so much. Bye-bye.
Holy hell! Pardon. All right. Anyhow, this is to give you an idea of where we've been, essentially, and now where we're going. Right. I'm running out of space, so I'll maybe erase this and just write what's coming here. Forgive me for that lack of space. All right. Really breaks my concentration, doesn't it? All right. Again, I'm no historian, but here's where we're at now. All right. We are, in terms of history, in this period. Right. Say 500 CE, which is you might call, if you're Christian, all right, 500 AD. To approximately 1500, right, CE, right. And this might be referred to as the medieval. Right, the medieval is the cutting edge of math, if you will. Right, and this is really why I was troubling you with this, is what follows algebra and arithmetic, what follows arithmetic, which is algebra. All right. And in terms of a revolution in thought, you might refer to this as basically being a derivative of logic, right? It's how shall I say, a balancing technique, or logical balancing technique. Okay, so you could, the whole point of my doing this, again, you're not responsible for anything. These dates are just, you know, my vague frames of reference. The point of this is to give you some feeling about how math sort of developed, right? You're not going to teach a little kid this, maybe, you know, but you see that there is a development there, right? I think it humanizes it, is what I'm getting at, right? We started with just our ancestry, right? Human ancestors, right? Just this idea of, you know, counting and then maybe using your fingers to do that, and then physically writing it down, and then applying operations, right? And then trying, you know, what are practical applications of geometry? Building projects, right? If you're making a house, or if you're making a pyramid, say, for example, right? It employs the concepts of geometry, right? Deductive reasoning, right, which is an offshoot, logic of geometry, was developed by the Greeks, right? And then famously Al-Khwarizmi, right, around 500, all right, wrote the book Algebra, all right? Algebra is it's if I'm understanding it correctly, reunion of broken parts, all right? A balancing technique, right? If you do a little bit more research, algebra is probably borrowed, just like Hindu Arabic numerals, from India at some point, right? But developed, right? I'm trying to think of the name. Brahmagupta was a person who lived in like 650, you know, or thereabouts, you know. And Al-Khwarizmi, who was really famous for the phrase, right? Right, algebra. Right. He lived in like 825. Right. All right. So anyway, think of arithmetic and geometry as being ancient math, right? And algebra, although it's been with us and it's still useful, is medieval math, right? And eventually, what will happen is calculus gets developed after this point, right? So like about the 1700s. All right. Moving on. Let me erase this. The blue is tenacious today, isn't it? Okay. Something. All right. I'm sorry. Let's discuss basically this diagram. There it is. And I'm going to sort of draw the same thing here to reiterate it, because I actually designed this about 16 or 17 years ago. So I lost the file that I believe that I had drawn that in. But let me try to improve it here. All right, in the subject of algebra, where we are, chapter 6, all right, there are two types of homework assignments that you would have, right? There is firstly algebraic expressions. What is going on? Really? Didn't I just... There's algebraic expressions, and then there are algebraic equations. All right. Now, what I encourage you to do is to think of this as basically being the building block expressions are the building block, and equations are more or less the house or whatever building that you're making. All right? And so think of expressions again as being the building blocks. Equations are the house. She's a brick house. Mighty, mighty. All right. Anyhow, insofar as they look very similar. I'm going to put a little sort of scribble here to separate. All right. Expressions can be, firstly, just a number. They could be just a letter, technically. Or they can be some combo, right? A combo that is tied together with an operation. So addition, subtraction, multiplication, or division is what I mean. Here are some examples. Something like the number 2, even standing alone by itself, is considered an expression. Right? Just the letter X, standing alone by itself, is considered an expression. All right? X plus 2, this is what I mean by a combination. Right? If you have these two things tied together somehow, sometimes this is like a number up in the front, or sometimes it's an obvious attachment like plus 2 or minus 2. All right? Or you could get something more complicated than that. All right? If you had 3 parentheses, x plus 2, something like that, or even further still, something like x squared, right, plus 7x plus 3. These are referred to as algebraic expressions, usually when they have a letter involved in them. All right. As a technicality, not to belabor the point, from the perspective of calculus, even the number 2 would be considered an algebraic expression because in calculus, a lot of times they attach a letter and then they'll just justify it by putting 0 here, right? X to the 0, assuming that the base x is not 0, is equal to 1, and 1 times 2 is still 2. All right. Anyhow, these are some examples of the building blocks. All right. Equations, on the other hand, might be better written or summarized by using the word expression. So I'm going to draw this. I'm going to write the word expression. I'm going to write it in 2 places. When you have an expression on one side of an equals, maybe a bunch of these, a combination of several, and then an equal sign, and then an expression, whatever it is, on the opposite side of equals, that is referred to collectively as an equation, right? The key feature here is that there's the included equal symbol, right? If you don't have an equal symbol, you have merely an expression. If you do have an equal symbol, then you technically have an equation, okay? Now again, why does the person care? well, they do technically follow different sets of rules, right? So even if they don't give you explicit instructions, you can kind of intuitively know what you have to do after a while, all right, just by glancing at that symbol or it not being there, right? There's also some terminology that you should affiliate with this and with this, all right? Use the word, reserve the word solve for when you are talking about equations, all right? It is more appropriate to say, I'm solving an equation, right? It may involve some other direction, right? But that is usually the objective, right? Reserve the word simplify when you're talking about expressions, right? Now, since these are the building block, you may end up having to simplify one side independently of another before you solve, but that's another story, right? There's another phrase here, which you may have heard, evaluate, right? Generally speaking, all right, if you see these instructions, evaluate or simplify, you're dealing with an expression, right? If you see this instruction, it means you're dealing with this, equations, right? Make that little distinction, right? Now, as for the actual procedures involved, let me erase a little bit here. I don't know why the blue is being so stubborn today. Let me draw underneath this, right? This simplifying. And next, what I'm going to put evaluate. When you simplify, this involves basically adding or subtracting, generally, like terms.
I hope I don't get anyone who's like screaming at me. Like I'm just like, fingers crossed, please. Please God, I'm like, I hope everyone's chill today.
That's the first thing. The second thing is that you might end up multiplying. You're going to multiply via something called distributive property.
And everything's verified. Do I need to put in a specific op that or miscellaneous? I forget. Yeah.
Distributive property is one of several properties I'm going to talk about in detail later. I'm trying to give you an overview right now. All right, so if you're adding or subtracting, you're going to be combining things that are like terms. There are conditions for that. And if you maybe have to multiply, then you're going to apply something called the distributive property usually. Right. If, on the other hand, you're evaluating, right, this really consists of doing two things. It means that you're going to plug in some given values in place of a letter. There's a phrase for that, naturally. This is called substitution. And then you're going to follow, famously, the order of operations. Order of operations. Right. The order of operations you're probably familiar with is, please excuse my dear Aunt Sally, is a mnemonic device for remembering the order, or Pemdas, right? Or perhaps more recently, GEMS is another version of Pemdas. Anyhow, it is a description of when you're supposed to apply operations. If you have operations of adding, subtracting, multiplying, and dividing, you may do those things independently correctly. But if you do them in a different order than everybody else, then you'll get a different answer, right? And answers have to be all the same in math world. Okay. Anyhow, we'll discuss the order of operations. Now, here's the real key here. When you're dealing with equations, right, you may, as a preliminary step, simplify each side independently, right? But that is not always the case. Sometimes it doesn't require that. What you really end up doing is these two things. You start to move stuff around, right? If you want to move something over equals somehow, all right, you end up doing opposite operations. And what makes it legal, and this is again, this is the revolution in thought, all right, that Al-Khwarizmi basically preserved for all time, all right? Balance, all right? This reunion of broken parts, right? You do this to both sides of equals. You can get away with murder in math, seemingly, right? You know, if you've ever done a very if you've been in algebra 2, or you've done some kind of complicated form of algebra, you may have seen, your teacher or whoever, start to rip numbers seemingly out of midair, right? And you go, well, geez, where did you get that from, right? As long as you do the same thing to opposite signs of an equals, everything is fair and square, right? I am fond of saying you can get away with murder in math as long as you're consistent. That is the balancing act. That is the gift, the Zen balancing act that is algebra, all right? It's a logical balancing act, all right? Do you perform opposite operations to move things over an equals? And to make it legal, you do it to both sides of equals, okay? This is different from the order of operations. The order of operations says pretty much that, well, if you are adding, then you are adding, right? If you're performing opposite operations, what does that mean? It means that instead of adding, very often you're subtracting, right? Instead of multiplying, what do you do instead? You're dividing. Instead of squaring something, what are you doing? You're square rooting. These are operations, and these are their opposites, right? They're equally important, but they're opposite in effect, right? Okay? Ultimately, the objective of solving an equation is to get something that looks like this. The look. You want something to be a letter equals a number, right? And nothing else, right? Something is solved for when you've gotten it down to just one sad, lonely letter on one side. It doesn't have to be the left, but it tends to be. And then on the opposite side, some sad, lonely number, right? Forever apart, right? Letter equals number. That is the goal. That is the objective, right? All right. Let me get a sip of water here. And I'll erase this. And let me turn on my camera too while I'm doing that, because I want to project. Oh, there we go. Come on. And I have to tell it to look for HDMI. Let's see. Oh, I didn't plug it in. That was stupid. All right, sorry. Here we go. I'm all flabbergasted, or what's the word? Discombobulated from the screaming at the, what you calls it? The credit union representative that I live with, you know. Hello, how do you spell your name? It's Z, as in zebra. Oh, brother. Anyhow, hopefully this is not too contrasting here. Well, actually, let me rephrase that. I hope this is contrasting enough to see. What I'm getting at is that I would like to project this image so that we can talk about the various names of the parts. All right? Here's a word bank that I made and a diagram to fill it in. All right, so let's do this together. The act of writing, not to digress, but since you're going into the field of teaching, presumably, all right, make sure that you get your kids to write, all right? I don't care, all right, when anybody tells you that is above you in the food chain, your principal, your vice principal, whatever, they can go straight to hell. You have to teach children how to write, all right? They need not to have one skill in lieu of another. They need to have as many skills as possible, and writing is the foundation of all education. So if you've been sticking with me through the history lesson, you know, writing is kind of important. So, you know, you can't just type is what I'm getting at. You have to write stuff, all right? I get frustrated when people say, the technology, the future, Yeah. That's right, and thank God for that too, because then we wouldn't be able to do this lesson remotely. But don't do one thing in lieu of another. All right. Anyhow, I digress. Sorry for the speech. Let's start with this. All right. You could probably figure this out yourself, but just to be clear, all right. Why do people get confused? Because there's a lot of names for the same thing. All right. English is inherently a confusing language for that reason. Right. Like, for example, a bar, all right? We have several words in the English language to describe a bar, all right? There's bar, inn, pub, tavern, all right? And I'm sure there's probably a saloon, you know? Where do all these words come from? They come from different languages that are the origin of English, all right? So English, unfortunately, is a language that has a lot of conflicting sets of rules, and that gets a math teacher in trouble. Anyhow, the fancy way of saying number sitting up in the front, right, taken from this word bank, is coefficient. So in this little space here, you could fill in coefficient. I can't, unfortunately, fit it because my hands, this marker is limiting me. But a coefficient is the way you would refer to this digit up in the front, all right? Notice that when you get to the X here, there's two boxes, because again, there's two different words to describe the same thing. It's looking at the same thing from alternate perspectives. So you could just refer to it as the fancy way of saying letter, which is variable, referring to the fact that it is something that can vary. Or you could look at it and label it from the perspective of powers. All right, notice that there's a 3 in superscript here. All right. In which case, this would be appropriately referred to as a base. Okay? It could be some other letter. It doesn't have to be a letter. It could be a number. All right? If it was the number 2, or, you know, maybe 4, something like that, all right, it would still be a base, even if it's not a variable. All right, now it's to the 3. Again, two labels to describe the same thing. Why? Because it has two different purposes. All right? Sticking with exponents, powers, the appropriate phrase here would be indeed exponent. All right? Alternatively, and this will be practical to us right now, you could refer to this as a degree. Degree 3 cubed, right? So, letter is a variable, really, to be more sophisticated. From the perspective of powers, it is a base, right? The number 3 from the perspective of powers is an exponent. Or you could, just referring to this vaguely, This is the degree, right? Now, again, lots of labels. If you're referring to the whole kit and caboodle, this thing, all right, it is most precisely referred to as a monomial, right? It is a monomial, and I didn't put the space for it, expression. Notice that there's no equals here, right? Mono as in one, right? Now let's look at this side over here. Notice that you don't have just one monomial. You have, in this case, it appears to be several of them, right? In a vaguer way, you could refer to these things separated by pluses or minuses in theory as terms, all right? And what will be more important to us now, that's a little bit hard to see. I'll put this in darker. Terms. There are these two that are of interest to us. 7x to the first and 3x to the first. These are referred to as like terms. You care because you can add or subtract like terms. Remember when I was referring to the instructions for simplifying expressions? What can you do with them? You can combine them, that is to add the coefficient 7 and 3, specifically, if in fact you decide that you have like terms. Now, what are the conditions of like terms? You have like terms when you have basically the same letters. They have to be the same letters and also the same degree. Now, legally speaking, you can add or subtract like terms, namely the 7 and the 3x, all right, because they meet this criteria here. And what do you actually do? You only add or subtract, all right, the coefficients, the fancy way of saying the numbers sitting up in front of the letter. So that means you're just going to add 7 and 3, which is really what number? 10x. The one that you see here I put to be very, very precise, but it is really an optional thing. One thing that is unfortunate is that math people tend to be lazy, right? For better or for worse. Lazy in a good way would be efficient, right? Lazy in a bad way would just simply be lazy. They leave out ones, as in the exponent here. They don't bother to write it. Or sometimes there's a coefficient, they don't bother to write it, right? They leave out zeros, right? They leave out positive signs, right? They do those in decimal points when it is a convenience to do that, right? So, if again, you were a teacher, set a good example, over-explain things. Put those features in because a kid won't see that they are optional, at least not immediately, even if you tell them, right? If you want, it's what's the word? Superfluous, but you could put 10x to the first degree, or you could just simply put 10x, it means the same thing. Okay? Now, this hanger-on over here, 5, this is referred to as a constant. All right? A constant is basically something that evidently doesn't have a letter attached to it. Again, from the perspective of calculus, they would actually put a letter there, but they would put a 0 attached to it as the degree. All right? Anyhow, this is a constant, which means that it really doesn't vary as the letter's x value can actually vary. All right. Now, the last thing are these two blanks here and here. All right? These collectively are referred to as a polynomial. You have a monomial, as in one of these, just one example, or you have a polynomial. Polynomials are monomials, or you can call them terms alternatively, separated by pluses or minuses. Right? It's a polynomial expression, technically, all right? And then it's in a certain form of etiquette. I have to quote. It's in descending order. You'll notice if you look at the word bank, there are two alternatives that are, these things that sound similar. Descending order and ascending order. Good etiquette. It's not really logical so much as it's about aesthetics, how things look. Pinky in the air, sipping tea, being very polite. Not telling your vice principal to go F. All right? That's not nice. All right? Descending order is from the, analyzing the degrees here. All right? Notice that it's highest in front, highest degree is 2. All right? And then it goes to 1 technically, and then it is technically 0. All right? It's going down. All right? You could write it jumbled. The 5 in the middle, the 7x on the end, whatever. All right? Or you could put it in descending or ascending order. They'd all be the same. They'd all represent the same quantity, technically. But good etiquette would be that you put things in descending order. I need water. There we go. Sorry about that. Anyhow, this is a little hard to see. All right, so if you're following along with me, let me just re-emphasize: coefficient, variable, base, exponent, degree, monomial. Technically, it's an expression. Right? These are alternatively referred to as terms, usually when we have them together in sequence: plus, minus, plus, minus, plus, minus. And these two specifically are like terms, which you care because, again, instructions. You can add or subtract these to simplify. 10 is simplified. 7 plus 3 is not simplified. Pardon me. This is also a polynomial expression. All right? Many parts as opposed to mono is one. If you've ever heard of, especially if you're a fan of history, all right, monotheism is belief in one God, right? Polytheism is belief in many gods, all right? Well, the root there, the prefix, mono and poly, refer to numbers as being many of these type of things or several of them, all right? Descending order is preferred, all right? If they don't give you instructions as to have something in any particular order, I would assume descending, all right? You're not going to be wrong, all right, if you don't put things in descending order, but it is more organized. And again, as the teacher, you have to set a good example. I'm not setting a good example by telling you to get in fights with your superiors, all right? But a little kid, all right, you're teaching them how to think linearly, all right? It is an invaluable skill for life, all right? Teach them to organize, all right? All right, now let's get into properties, and I'll turn this off. Insofar as properties are concerned, there are many properties in math, but the three that I have found to be invaluable in the subject of algebra are these three. So let me give you these. There is commutative property. And then there is associative, which are very similar. And then later on down here, there's distributive property. This is an example in my own life, right? I remember being told about the commutative property in maybe 3rd or 4th grade, and then again in junior high, middle school, and then at some point in high school. And it never, like, they just said, here, write this down, and I went, oh, okay, whatever, just don't yell at me. A plus B equals B plus A. Or the alternative is A times B equals B times A. They had told me many times, my teachers, all right, write this down, all right? And I went, okay, but I never really understood, for whatever reason, what the point of it was. When I became a teacher, it finally dawned on me, as it might dawn on you, all right? What it is basically saying is this. The arrangement doesn't matter. That's not the most eloquent way of speaking, but it really does get at the heart of what is being stated here and here. You can have this feature in front. You can have this letter B in front. And they will be equal no matter what, right? Now, truth be told, this only applies to addition or multiplication. There is no commutative property of subtraction, which means order does matter in that case. The arrangement is very important. Similarly, there is no commutative property of division, which means that the arrangement is very important in those two cases. But when it comes to adding or multiplying, you can get away with arranging the pieces in a different order. All right? When you're deciphering a word problem, that is, you're translating it from something verbal purely into something that is symbolic, all right? You could take advantage of the fact that there is a commutative property and put things in an order that you find convenient or that you find comfortable, all right? But when it comes to subtraction, especially, and division, especially, there's no commutative property. So it's really those instances where there isn't one that you need to worry, right? Here's an example. If you had 1 plus 2, you get 3. If I switch the position of these two things and put the 2 in front, I would still get 3. If I add 2 times 3, I would get 6, right? And if I switch the position of them, 3 times 2, I would still get 6, right? Order doesn't matter when you are just adding or if you are just multiplying. That's the point of the commutative property, all right? There is similarly the associative property, which looks like this. Usually involves 3 things. A, B, and C. Let me try to fit this. A, B, and C. And they'll be separated by an equal sign. And in the first instance, we'll just talk about adding. And then here's one with multiplication. All right, now, this is again saying this. It's saying that the arrangement really doesn't matter, all right, also. But it is talking about grouping. So like you might see parentheses, all right? Perhaps if you decided to group these two things first, this is about grouping. When you put things in parentheses, that's drawing focus to those things and saying that they're important. They're the most important and you should deal with those things first, all right? Locking your focus, like, this is cruel, I don't like horse racing, but like, they put blinders on a horse, right? So they don't get distracted. Well, parentheses is like having blinders on your student. Look here, kid, all right? And focus on this stuff, all right? You could, in theory, add these two things before you involve this third thing. Or you could add these two things before you involve this third thing. Or there is, in theory, A and C grouped together, all right? Similarly, These two could be multiplied first, or these two could be multiplied first. Right? This is essentially saying, again, the arrangement doesn't matter. You're going to get the same sum in the case of adding. You're going to get the same product in the case of multiplying. But perhaps a more eloquent way of saying it is that you could group at your convenience. Right? Notice that this is just for adding or multiplying specifically. Right? Now, if you're dealing with distributive property, you might see two models that look like this and this. I'm going to draw a line here, a squiggle, to separate these from the distributive. The distributive property is something that looks like this. A, B plus C, or you might see A, B minus C is equal to AB plus AC, and this is AB minus AC. Now again, why these letters A, B, and C? These are called models. All right? They're a pattern basically that an actual example simulates. Right? These models are meant to simulate an actual example, right? And a generalization, right? You would have potentially a number here, here, and here. Anyhow, you can use this distributive property when you're dealing with arithmetic, whereas that there are no real letters involved. There's no actual variables. It's just a 1, a 2, and a 3. But where it is really practical is when you're dealing with algebra, which is why I say of all properties, these three are the most important. All right? If you can't actually add, all right, then what you could do to sort of simplify is at least get rid of these parentheses. And the way that you do that is by distributing the A via multiplication to each of the contents of the group. Right? If you can't subtract, as in this case, you could at least multiply and write the expression, right, as the product of the contents and the thing on the outside. You've distributed essentially the outside thing to each of the inside things. All right. Now, again, this can be applied to arithmetic if it is a convenience for you somehow to multiply rather than just add or rather than just subtract. You have that legal option to do that. All right. But it's really more practical when you're dealing with algebra, which is what we're doing now. One last tidbit of information before we get into some examples. Let's discuss the order of operations. All right, the order of operations, this is again something that you apply to expressions. Whether the expressions happen to exist as part of an equation is another story, right? But the order of operations is primarily, consistently for this. All right, now you might have learned them in one of two ways, right? The order of operations is the correct order in which you multiply, add, subtract, and divide. And things that are more complicated than that. You may have learned an acronym, or you may have learned this mnemonic device. They're both mnemonic devices, really. But this is more specifically an acronym. Right? Usually, as a person who's been teaching math for a while, people come to me with Pemdas, right? At least in the United States, right? Pemdas, right, is an acronym for basically doing things that are in parentheses is first, doing things that are raised to an exponent second, right? Doing multiplication or division, doing addition or subtraction, right? And there's nothing wrong with that. That's totally cool. Just one thing that you have to convince yourself of, and especially impart to a little kid who has never seen this before, maybe an older kid too. These concepts of multiplication and division are equally important. Because they're opposite concepts, right? Similarly, addition and subtraction are equally important because they're opposite concepts. So, which do you do first? It depends on the problem. A lot of times people erroneously will go, oh, it must always be adding before subtracting. Not so. It could be subtracting is first because it depends. You do whichever is most left, or leftmost. That is, that direction is what I'm referring to. Again, I've had people who will fight with me over this and go, but the letter A is on the left. All right, yeah, in the mnemonic, all right, in this acronym, all right, it is. But that's just to get you to remember it, all right? If, like in English, right, we use a lot of vowels and stuff, right? So if we put the S here, it wouldn't be as eloquent or easy to say, all right, as an acronym, all right? I like this better, this alternative mnemonic device, which is to use whole words to remember the order of operations. This is what I was taught by my dear third or fourth grade teacher, Miss Cabilio. All right, I believe it was. All right, it goes like this. Please excuse my dear Aunt Sally. Now you might say, I don't have an Aunt Sally. And you're right, I don't have an Aunt Sally. All right, I wish I did. All right. Because then I would find excuses for her all the time. All right, and she would find them for me, I hope. Anyhow, so I digress. I like this better because it puts things on steps, right? Tiers, if you will. You know, like if you've ever watched the Olympics, the person who gets the gold usually is on the highest tier, you know, or the highest step. You will do things in parentheses, as in please, the initial please is, the initial is P, right, as in parentheses. All right, first, you must always do that first. Again, it's like putting blinders on a horse. When you wrap something grouped in parentheses, it's trying to draw your focus. That's just saying that this is the most important thing out of the whole slew of things to do, because you must deal with this group first. All right. Excuse is, again, as in something raised to an exponent. so a slightly smaller font, a little bit higher, a superscript. All right, this is something that you must deal with second. All right, then there is multiplication and division. All right, these are things that you do third. All right, and then there's Aunt Sally, is addition and subtraction. All right, which you do last. All right, now, there is still the issue that people make, right? They go like, well, my is before dir, right? And the same problem with M before D and Pemdas. And they go, therefore multiplication is always before division. Again, not true, right? As you can see, they're on the same tier, right? So they're equally important. They may be opposite concepts, but they're equally important. So once again, when confronted with deciding between doing a division or multiplication first, you have to decide on the problem at hand. So you do whichever is leftmost in the problem, right? Same thing with adding and subtracting. They are on the same tier. So you do whichever is leftmost in the problem. Okay? There's another one I had heard of recently as far as acronyms are concerned. And it's GEMS. Just kind of cool, right? This is a little bit more concise though. It doesn't tell you the initials of everything, it merely implies them. GEMS is, instead of referring to something in parentheses as P, it's referring to the group contents, but it still means parentheses. Sorry, I think my curtain here is failing. E is in exponents, and then when it comes to multiplication and division, it just sort of pairs them together under the abbreviation M. Right, and subtraction, it just pairs addition and subtraction together onto S. Right. Anyhow, keep a broad mind always. Right, not one thing in lieu of another. All right, both. All right. I personally prefer this because again, I think it emphasizes that there are steps involved here. All right, there are tiers of importance, and just to sort of tie everything together with a nice big string. Think about the development of math, right? Counting came first, right? A slightly more sophisticated form of counting is adding. A slightly more sophisticated form of adding is multiplying. A slightly more sophisticated form of multiplying is exponents. It's multiplying in a peculiar way, right? So there's a development, right? And this is the foundation. So when you're dealing with expressions, right, if you have to simplify them, you do things in this particular order. There is one weird sort of situation. I don't think you're going to see it too much, but I'll put it here for reference. Here's a little thought balloon. Right? If you have something that is referred to as a rational expression, a rational expression is a glorified fraction. So there's an obvious top and an obvious bottom. This is the only instance in which you might sort of deviate from this. What you should do is simplify the top first, simplify the bottom, what would be something like a denominator, second, and then divide top by bottom, if it is possible, last. Right? In the top, there may be multiplication and division. You do them as they occur. But this line is division between the top and the bottom. Again, you do that particular division last. Okay? That's only if you have a really complicated problem. That is a complicated top and a complicated bottom. Deal with the top and the bottom independently, And then if you can simplify them by dividing, do so. But do that as an afterthought. That particular division, this particular line separating the top and the bottom, do that last. Alright, now finally get to some examples. Again, if you're not happy with my explanation, and I wouldn't blame you, right? I tried, but I'm no saint, right? I'm not perfect, right? You always have this reference. Again, you bought the ebook, so this is where I stole it from. I just tried to make it easy to print it, all right? Let's do some expression simplifying. Let's see. All right. Here we go. Blue is giving me trouble today, so I'm gonna lay off the blue. Here's black. All right. Here's an example. They will probably give you the direction simplified, but again, with enough experience, you probably can tell intuitively. You should always read instructions, of course, but if they don't give you instructions, you could probably intuitively know what to do as long as you can identify whether you're dealing with an expression or you're dealing with an equation. So, for example, if you had to simplify 3x plus 6x, all right, ask yourself this every time. Right? Is this an expression or is this an equation? Right? If you identify it correctly, there's no equal sign in here at all, right? This is an expression. Therefore, what should you do? You should then ask yourself, well, what kind of terms does it have? Does it have like? Or does it have unlike terms? And again, if you decipher it correctly, you go, well, indeed, they all like. How so? They are the same letter. So far, so good. They're both x's, right? And this is the second criteria, which you may not have to worry about too often, but I would check anyway. They're the same degree. Means that the exponents are the same. This is technically degree 1 and degree 1. Right? Having identified these indeed as like, that means that you can add or subtract, if necessary, the coefficients. That is the numbers sitting in the front. Now my black is dying, huh? Okay. So, these are indeed like. All right, so let's just add 3 plus 6. What do you get? 9 with an x attached to it. And that's it. Right? Do you have to put the 1 here? No, it's totally optional. If it helps for the sake of clarity to have it, then go ahead and put it in. There's no sin in doing that. All right? It is considered more concise if you don't bother. Right? Especially when you're just comparing them for degree, that it's an issue or that it's important. Okay, here's a more complicated one. All right, suppose you had to simplify negative 3x plus 2, a jumbled mess, minus 5y plus 10 plus 2y plus 4x. Now, a big jumbled mess doesn't appear to be in descending or ascending order. It's just a mess. All right. There, I'm telling you that you have to simplify. But again, if you didn't see an equal sign, you would go, all right, well, it's an expression. So what could I do? I can simplify an expression. All right. What does that mean literally, though? It means you can compact it together so that it is less ugly and more organized than it was given to you. Right? There's a good sort of maxim for life. All right, a motto. Leave everything better than you found it. All right, that's a little bit harder to do when you're dealing with a public bathroom, of course. But do try, you know. Anyhow, leave things better than they were given to you. All right. What I do, so that I try to avoid making mistakes. If you, especially as a teacher, right? A lot of times you have to make your own answer keys. All right. You have to double check and triple check everything, right? I do this. I encapsulate, right, things that I know are like. So starting from the far left here, I'm going to circle this negative 3x here, right? And yes, I would group the sign as such, right, immediately to the left of the number 3. And then look for its buddy here and encapsulate that. And then sort of link them together. And then write what I predict the outcome would be. Now there's an issue of integers here, so you may be a little rusty. Let me remind you. There's rules, again, conflicting sets of rules depending upon what you're doing. If you're adding or subtracting, right, these are the rules. Same signs, then you add. If you have one of each, then you subtract actually. It's the sign combinations that dictate the operation. So you have one negative, you have one positive technically, you have one of each. So what are you gonna really do? You're gonna really subtract them, all right? In spite of that positive sitting there, right? So what's 4 minus 3? It's 1. Okay. I'm gonna purposely write the 1 for right now. It doesn't have to be there. What is the letter in common here? It's an X. All right. Then there's the sign of the answer. All right. The sign of the answer, the outcome. Let's see if that works. Is that visible? Barely, right? Try that one. Matches. That's even worse. Matches the larger magnitude. I have to say that even though I don't like to. Magnitude. All right, now, magnitude has to do with the size of the number, right? Its distance from 0, right? Think of it as being the digit, the bigness of the digit, for lack of a more eloquent expression. All right? Which had a larger magnitude, the positive or the negative? This is a larger magnitude 4. It is more distance from 0. So since it was positive, your outcome is positive. And if you don't like writing, I'm going to just move this for a moment and turn that slide on and see if that helps. If you don't like writing positive 1, you could just simply write positive x, and it means the same thing. Right? Then, when I'm looking for the next thing here, there's a constant here. I'm going to just opt for a different shape here. So I'm going to encapsulate this in a little box. Right? And then look for what matches it somehow. What else is a constant? Plus 10. And group them together, tie them together. All right, that'll be the next thing here. Same signs, so I'm going to actually add. Right? 2 plus 12 is positive, 2 plus 10 is positive 12. okay? Which again, you could simply write as just 12 here, plus 12. In sequence, we can always rearrange them later. And that leaves the last two, which sometimes end up combining and sometimes not. Running out of shapes here, so I'm going to use a triangle. Minus 5y and positive 2y are like terms. So legally speaking, I could add or subtract them. Which one do I do? Analyze the combination here. They're one of each. There's one thing that is a negative, one thing that is a positive, so I'm going to actually subtract them. And that means that I'm going to get, as far as a number is concerned, a magnitude, it's going to be 3 with a y attached to it. The sign of the outcome matches the larger magnitude. The larger magnitude is a 5 that is more distant from 0. So therefore this is a minus 3. Right? And you could write it like this, or you could put it in alphabetical order. Right? Oftentimes that's what happens. In alphabetical order, you would have this. X minus 3y plus 12. And that would be considered the most concise way to write the original gobbledygook here. You have simplified it because you made it shorter. Okay. Alright, this is a little burdensome here, so I'll leave the light on for a while. Let's see if this improves things. Not really. Okay. Alright, let's evaluate and then we'll shift gears here. Here's an example of evaluating. Still dealing with expressions, just a different procedure. Remember, when you evaluate, you're plugging in and following the order of operations. Right, strictly. So if you're going to evaluate, say, for example, this problem. Negative x squared plus 3x plus 10 when x is 2. Okay. What I do is a good rule of thumb is to rewrite the example. So I'm going to do that here. Negative x squared plus 3x plus 10, and then, even though it's not included to begin with, draw your own parentheses as wrapped specifically around the letter that you're substituting for. So there's x's, all right? And you would do it like this. You wrap a parentheses around the x here, negative on the outside, and you wrap a parentheses here. All right, in a way, you're creating sort of a pocket that you're going to fill with the number that you're substituting. So if x is equal to 2, and if they say is, they mean equals, right? You're going to stick a 2 here and a 2 here, right? Now the reason that I consider this important, all right, as a procedure is because notice that there is an exponent here and there is a negative here, right? If you're substituting in this particular problem for x, the exponent is not really affecting the negative that is here. If you were substituting negative 2 instead, then that 2 here, this exponent would be affecting the negative as well, but it's not. It's outside of it. Anyhow, you have exponents, you have regular multiplication, and you have addition and some perhaps subtraction. Which should you do first? If you follow the order of operations rigidly, and you should, right, at least to get started, all right, you should do the multiplication that is exponents, the amped up version of multiplication that is exponents first, which means your focus is here, right? And what you do is you write an algorithm. An algorithm is a step-by-step thought process that you're writing out. Again, I don't want to belabor the point or make anyone feel bad, but as a teacher, as one to another, don't ever tell your students not to write something, all right, when it comes to math. You can't read somebody's mind, all right, unless you have some kind of superpowers, all right? So how do you see somebody's thoughts? They write them, all right? And especially when it comes to math, right, you can see where they make a mistake if they write their thought, right? And therefore you can help, right? If you teach a kid, oh, you're gonna do everything in your head, that's being a fool, all right? It's great that a person may be able to do something in their head, but when you're dealing with little children, they're not geniuses, all right? And in spite of what their parents may think, right? You have to make them geniuses, all right? So teach them how to express themselves verbally, all right, and physically, literally, all right? Write what you're thinking, right? So that the world can see, right? What is 2 squared? 4. Now, write all the junk that is left over next to it. Even if it seems arduous, even if it makes your hand hurt, even if it makes it seem superfluous and unnecessary. Do it, all right? You're teaching people to think linearly by making them write. There's a negative here, right? There's all this junk here that's still left over that you're still going to deal with. And you're going to decide what to do next in your line of logic. All right? So, next thing. Your choices are now between adding and subtracting, maybe, regular multiplication, or again, maybe adding and subtracting. Multiplication takes precedent over adding and subtracting. It's higher in the order of operations. So therefore, your focus is now here. All right? This is a fancy way of saying multiply. You're distributing. All right, 3. What's 3 times 2? 6. Write that. Write the junk that is adjacent to it. There's a -4 here, there's a plus here, and there's a plus 10. All right? It's a little sloppy, sorry. All right, now, what do you have left over? You have maybe some adding and subtracting depending upon the combination. Maybe some adding and subtracting depending upon the combination. Which should you do first? According to the order of operations, regular adding and subtracting are equally important. Which should you do? The leftmost. So specifically, your focus should be on the 4 and the 6, not the 6 and the 10. Might you coincidentally get the same answer? Maybe. It depends on the problem. But again, the operative term there is coincidence, all right? You want to get everybody to the same finish line, all right? So, one of each sign, you're going to subtract, really. In your next line of thought, if you subtract these, you establish the digit 2. What is the sign? The sign will match the larger magnitude sign. So 6 is a larger magnitude. It's further from 0, and it's a positive. So this is a positive 2. And then there's this leftover junk here, 10, right? Next line. You have nothing else to choose from. You're going to have to just do this. So your focus is lastly on these 2 things. What is 2 plus 10? 12. And you can put a positive or optionally not, right? Again, I'm not trying to belabor the point or make anybody feel bad, but in the position of teacher, you have to make sure that children know how to express themselves, right? How do you help them unless you can communicate? The easiest form of communication, right, is written, right? Whether a person is deaf, right, or they're born with their hearing, right? As long as they can see, right?
No, you're staying here.
Right? You can communicate, and you could make little tweaks, right, to whatever their work is. If you just go, at this point is where the error occurs. Don't feel bad about the error, right? But fix it, right? Writing is very important. It is not an archaic skill that we should just throw away, all right? There are plenty of dodos, all right, in this state, New Jersey, who have decided that writing is not important, all right? Never support one skill in lieu of another. Establish many skills. Get frustrated, I'm sorry. All right, it's very important. To me, it's a disservice to people to tell them, oh yeah, you don't have to do that anymore. No, you need to know how to type. You need to know how to code. You need to know how to write. You need to know how to write in script. You need to know how to tell time. These are all important, all right? Depend, at different facets of your life, maybe, but they're all equally important, right? No, math is not more important in history, literature is not important than gym class, right? Be a Renaissance person, refine all of your skills. Now let's get into equations. Make a mess here. All right. Now, in the subject of equations, shifting gears here. Before we get to the process involved, and you'll see again the distinction between the different sets of rules, there's also the answer, right? And how you present the answer and what the answer is referred to as. So I'm just going to simply draw a diagram to illustrate answers. All right. Answers can be anything, right? They can be true, right? Or they can be false. However, only one of them is an actual solution. The things that are true are referred to as solutions. Okay? And again, if the objective in the long run of solving an equation is to get it to look like this, letter equals number, right? One letter, an equal sign in between, separating the sides, and then a number. You've solved for the letter when you have that situation. You could, the intuitive thing is to go, all right, well, x equals 5, say, for example. After you go through your procedures, you get it down to this letter is equal to this specific number. And it's usually what we're brainwashed is to look at it this way. Just beware that there is a fancier way of writing the answer. And oftentimes it looks like this. They will draw these fancy curly braces, and they will just simply plop the number 5 on the inside. This is just fancier way of writing solutions, right? When you have no solution, the situation where there is no solution, there are two ways of writing that, right? I wish green was more cooperative. You could either write, if you're using set notation, which is what these curly braces are called, you can just simply write an empty set, or you could use this symbol, but it looks like a no smoking sign. It's not 0, it's called null, right? Right? It purposely has this cross out that overextends past the edges, just not to confuse it with a regular 0, because 0 is a number, all right, and 0 could be in fact a solution to some specific problem, all right? Anyhow, don't put this in here, all right? Just either draw an empty set if you want to be fancy, or draw that, all right? Then there's this situation where you have all real numbers, right? You may have heard that expression, right? Here's a thought cloud. All real numbers. A lot of times, again, if they're being fancy, they'll have this sort of Great Gatsby-esque style R. This means all real numbers. It means that anything is possible, anything works. Okay? Just beware of that. It's not really the most important thing, but it's just mentioning it in case you see it. All right, and then you go, geez, what does that mean? It looks like alien hieroglyphics. All right, it's just a fancy. This is just a fancy way of saying that. All right, and these are just fancy ways of saying that there's no answer. All right. All right. Now, let me pull this out. This sheet, which again is just an alternative way of writing something. You don't have to do it this way. If you have, this is another thing. Don't rob a kid of their comfort. All right. If a kid knows how to do something, that's good. Right. It's a blessing. Right. But just make them aware, you know, that there are alternatives, there are options, and in the long run, you get to choose, right, which is most convenient, all right, for you or for the problem. All right. I'm going to turn my projector back on, and hopefully this will cooperate. I'm going to turn this light off. Let me switch slides here. That. This is just a suggestion. If you have a way that you were taught to write out equations, I would never fault you for using that. But I can tell you that this is what I do personally. All right, so we'll leave it like that. I think it's a little bit more compact way of writing, and it kind of gets you your feet wet, gives you a feel for solving by applying opposite operations consistently, right, between two sides. So think of this as sort of being like a scaffolding for the building. Just an option, just an alternative way of looking at it. Here are the types of problems that you would see. We'll start with these. How many have I got? I got 4 here. All right. That's probably for the best. Let me just do these 4. All right. This will be an example. This is an example. And then these 2 to start with. And then I'll erase stuff. All right. What you might refer to as the one-step equations. One-step equations have one step because there's only one operation to deal with. So for example, x minus 8, and then there's a 12. And then x plus 11 is 19 maybe. And then this one is a little bit more awkward. I'm going to put a line here, 4. All right. And then there's 7. I'm going to complete this thought here. 8. All right. And then 7x equals 35. Okay. Now, if you at this stage in your life can look at this and go, I already know what the answer is. Good. All right. But your job is to not know what the answer is. Your job is to have a system for figuring out the answer when you don't know what the answer is, just intuitively. Intuition is a blessing, and I would never try to dissuade a person from having intuition, especially when it comes to math. It's a blessing. But having a system is more powerful because you can apply it to any unique circumstance, all right? Rather than just things that are intuitively memorized, right? a kid will resist you, especially in 6th grade, if I'm like, I know what the answer is. All right? I don't care if you know what the answer is. I'm trying to teach you a way to figure out the answer even if you don't know intuitively. All right? So here's what you do. You draw a little table like this. You don't have to do this, but it works for me. All right? And realize that if you're going to solve for the letter x, that you need to move things away from x. So how do you go over the equal sign? You perform opposite operations, not the order of operations, opposite. Anytime you move over x, you're performing an opposite operation. What is the opposite of subtracting 8? Adding 8. As I am fond of saying, I repeat, you can get away with murder in math as long as you're consistent, right? If you want to add 8 suddenly, for whatever reason, here, on this side of equals, fine. But make sure that you do it here as well, all right? The effect of performing opposite operations, this is a negative and this is a positive here, is that they cancel. All right, that's the whole point. You're trying to get the letter alone here. You're trying to get this to look like letter equals number. That's the objective. Right? It's solved when you've gotten the letter isolated on one side and just the number on the opposite side. So what's left over? X. You don't have to put 0 here. It's optional. Then you actually add these. What's 12 plus 8? 20. And that's your answer. All right. Here's the next one. In this case, you want to solve for x by moving 11. Again, if a person can do this in their head, great. All right, but you have to be able to show another human being what you're thinking. All right. So, and just talking at them doesn't work either, especially a little kid. Let me tell you something. You ever try to talk at a little kid, they won't listen to you. All right. What's the opposite of adding 11? Subtracting 11. We'll use red to be consistent here. Minus 11 in this case. So it started out as a positive, started out as plus 11 addition. In order to justify moving it over equals, I do the opposite operation, which is subtracting 11. Right? By design, when you do perform opposite operations, there is a cancellation effect. That's what you're hoping for, right? You can put a 0 here if you want, but it's superfluous. You don't have to write it. Again, this is an example of being lazy or being efficient. Well, being efficient is really more the case. All right, this is x that's left over. And then you have 19 minus 11, which is a regular subtraction problem, and you know the difference is 8. All right? This is your answer to that type. The book will probably refer to this as, applying the addition property. I don't think it's really necessary to subscribe a name to what you're doing here. In a general way, you are just performing opposite operations, so opposite of whatever you're given. So if it says minus, you are adding. If it says plus, you're subtracting. That's usually the hurdle that is difficult to get over when you're teaching kids in junior high, middle school, whatever you want to call it. All right? And they go, you just been telling me all these years that this sign means to add, and now you want me not to? Yes, because it's algebra. It's a balancing act. It's a procedure that you're learning, not the answer that you're learning. All right. Now, down here, again, you're still going to do the same thing for these one-step problems, but what are you starting with here if you see this line? This is a fancier way of saying divide. All right, it's the rational way of writing division. You know how in the case of division, we have the division box like that, where there's a number inside and outside, or the fraction-esque style of writing it, where there's an obvious top and an obvious bottom, or the colon with the line through it. At least in the United States. In other countries, a lot of times they just put a colon. All right. Well, this is just an alternative way of writing division. So, what is the opposite of dividing by 4? Multiplying by 4. So just not to confuse it with the x here, that is the variable, I'm going to use the optional symbol for multiplication, which is a dot, right? And then I'm going to put the number here, 4, right? Slightly above it. You don't have to put this 1 here, but that's really the justification. This is 1 over 4 and 4 over 1. They're reciprocals. And just say to yourself, well, to multiply something that is divided by the same magnitude, 4, would be to induce a cancellation effect. In this case, the cancellation effect would not produce a 0, as in the case of adding or subtracting. It would produce an outcome of 1. Do you have to bother writing 1 here? You can. It's not wrong if you do, but it's superfluous. You don't have to write that, right? Anyhow, you can only legally speaking get away with this if you are consistent. So if you're trying to move 4 from here to the opposite side, you do it by opposite operations. The opposite of dividing by 4 is to multiply by 4. If you did it here, your hands are tied. You're obligated. You have to do it here. All right? So what is left over? X. What's 4 times 8? 32, right? No sin in using a calculator either, but in the long run, encourage your students to memorize the multiplication tables. It makes a person more strategic if they have that intuition. That's the thing that in the long run you would want someone to kind of have in their head. Don't get mad at them if they don't. All right, that's being a bad teacher. All right, but encourage certain things. All right, memorizing multiplication tables makes a person strategic. It is also a frame of reference for when you're dividing. It's very important. All right, now again, this is what operation to start with. It's a little hard to decide sometimes. If two things are pressed together like this, and there's no obvious symbol in between them, you assume that what is going on here is technically multiplication. And I'm going to opt for the dot rather than the standard x because I don't want to confuse it with the variable. If I want to justify moving 7 from here to here over equals, I'm going to perform the opposite operation. What is the opposite of multiplying by 7? The opposite of multiplying by 7 is to divide by 7. And if I did it here, again, my hands are tied, I'm obligated to do it here. Right? There is a tendency in algebra to not use the colon with the line. It is just to use this bar. Okay? It isn't wrong if you use that, but this is a little bit more compact. Right? So anyway, the effect once again, when you perform opposite operations, is that it induces a cancellation effect. It's different from, again, adding and subtracting causes 0 to occur. All right? Multiplication and division cause 1 to occur, which you don't have to write. Right? And then you have an x left over, and then you're going to simply divide these. 35 divided by 7 is 5. All right. Now, these are again the basic tools in the set of tools for solving equations. One-step equations, opposite operations, opposite of, come on, opposite of adding, opposite of subtracting, opposite of division, opposite of multiplication. Just having that vague awareness is superior, I think, to be able to cite the property. All right. Sometimes you don't have a name for it. All right. This is first and foremost a balancing act. All right. Algebra. Here's a slightly more complicated problem. And I need this space, so I'm going to erase this. All right. Suppose that it wasn't just one step, right? Suppose you had something that was, let's just say, 2-step, sounds like a dance, right? Or even worse than that, multi-step. Here's your example, and here's another example adjacent. All right. 3x minus 5. This is a little bit off the page. Sorry, I should lower this. There you go. 3x minus 5 equals 28. Again, a kid might say to you, I already know what the answer is. I did it in my head. And that's great. It's a blessing if you can do it in your head. But encourage them nonetheless that they're not learning the answer. They're learning a procedure that will help them get the answer when they can't guess correctly. All right? When it isn't intuitive. All right. Now, usually, all right, I'm going to put some extra thoughts here. Usually, what you do is you do the addition subtraction part first for an equation. All right, this is not just an expression. And then you do the multiplication and division part second when you're dealing with an equation. There are some times when you have to, as a preliminary step, sometimes, right, you have to simplify each side independently first. Independent. I always had trouble spelling this for some reason. First. Right? And that is basically you follow rules for expressions. Right? Because you're dealing with expressions. You're dealing with the building blocks before you're dealing with the house. In this case, you can't simplify anything. If you have it basically that you have letter plus or minus number equals number, then you're good to go. Right. What you see here, 3x minus 5 equals 28, is basically that. You have something with a letter, then plus or minus some number, and then it equals just a number on the opposite side, in which case you're going to probably start with this situation. There's no simplifying necessary. So I'm going to move the 5, right, from here to here over the equals. And when you move over equals, you perform opposite operations. What is the opposite of subtracting 5? You add 5 here, and you add 5 here to make it legal. The effect of adding 5 to its negative opposite part in here is that there's a cancellation, right? It would technically be 0, but we're not going to bother writing that. I'm just going to scoop this over 3x. 28 plus 5 is 32. 33 rather, right? And now you have a second step because this is a two-step. If again you have things pressed together, you assume that they're starting out as being basically multiplied. So if you want to justify moving 3 from here to here over equals, you do the opposite of dividing, the opposite of multiplying, which is dividing. That is to write this bar here, and to make it legal, you do it to both sides. Okay? This is the Zen balancing act that is algebra. All right, so what's 3 divided by 3? 1. Do you have to bother writing 1? No. X is left over, that's what you wanted. What's 33 divided by 3? 11. That's your answer. Okay. Now here's a situation where you may have to simplify first. All right. I'll put this here. 6x plus 11, and then a lot of extra gobbledygook over here. 2 times parentheses, x plus 6, and then minus 5. This would best be described as multi-step because it doesn't just entail 2 operations opposite, but a lot of sort of preliminary work cleaning it up. What you're going to try to do is, I'm going to get rid of this just for the sake of space. You're going to try to get it to look like this. worst case scenario, letter plus or minus number equals letter plus or minus number. And right now you don't even have that. You have letter 6x plus 11, but then you have this thing with parentheses here. So, put the blinders on yourself. Your focus is on the side that isn't quite right? It isn't just down to a letter or something with a letter plus or minus a number. It has some gobbledygook here. And then you notice that there are parentheses here. So we're going to deal with this expression before you start moving anything over equals. You're going to try to compact this down to this slightly more ideal scenario. How so? If you look at the inside of the parentheses, you see that they're not like terms. One is a letter x and the other thing is a number 6. So you can't immediately add them even though it says plus in between them. So what can you do? You can dismiss the parentheses by distributing. Right? The distributive property finally shows up here. Right? And you do the operations as they are stated. There's no opposites because you're not pulling it over equals yet. Distribute 2 to the x, distribute 2 to the 6, right? So, 2 times x is 2x abbreviated, right? 2 times 6 is plus 12, and there just happens to be this minus 5 sitting adjacent here. Still not quite ideal, so what you're going to do is then mush these together, and you would end up with this. 2x plus what? One of each sign dictates that you subtract. That will establish the digit of 7. The sign of the 7 is positive because it matches the larger magnitude number. So this is as concise as you can get it. 2x plus 7. Now you play the game of algebra. You perform the game of arithmetic, and now you're going to play algebra. So I'm going to write this next to it. 6x plus 11. And I'm just going to draw myself a slightly elongated table here and continue. Just not to be distracted, I'm going to erase this stuff here. All right. Now, you don't have to put letters on the left, but that's kind of the normal situation, for lack of a better phrase. So what I would do is bring this 2x over to here and bring this 11 over to here. You get things that are exclusively with a letter on one side and things without a letter exclusively on the opposite side. Again, it doesn't matter if it's on the left or the right. I like the left personally. How do you justify moving this whole chunk, this whole term? What is the sign if it's not written what you assume it is? Math people leave out ones, zeros, decimal points, and positive signs. So if there is no sign here, it means that it was optional. So now I'm going to purposely put it there to make it easier to decide how I'm going to move it. The opposite of positive 2x is minus 2x. And you might say, well, I don't know what x is. It doesn't matter. By sheer logic alone, you can justify cancellation because it's something, even something mysterious, minus itself. And I could move it by performing opposite operations to both sides. So I'm going to take this thing for this reason to cancel it, and then plop it over here where its buddy is. Right? What's 6? This is a positive 6. This is a negative 2. They're like terms. So you can, legally speaking, add or subtract them. What is 6 minus 2? 4. With an x attached to it. What's still here? 11. And over here, 7. If at this point you have decided for yourself, and I'm kind of corrupting your opinion admittedly, you have decided that the things with letters are on the left. Now you have no choice. Now you got to bring this 11 over here. And you do that again by opposite operations. The opposite of adding is subtracting. And I'm going to elongate this. and I'm going to strategically park it under here where it has a friend that I'm going to mush it together with. All right? So, these cancel. What are you left with? You got 4x. And then one of each sign dictates you subtract. Come on. One of each sign says that you suggests that you should subtract these. So you're going to establish a digit of 4. What a coincidence, right? And then the sign of this 4 is matching the larger magnitude. So if the larger magnitude is negative because of 11, then this is really a negative 4. Right? Last step. If it is understood that these two things pressed together, 4 times x are really being multiplied. If I want to finally finish it, right, I'm going to move just the 4 from here to here. Over equals. Over equals is always opposite operation. So opposite of multiplying is dividing by 4, dividing by 4. Right? This again, by design, intentionally, a cancellation effect. What is left over? X equals negative 4 divided by positive 4. There's a different set of integer rules which you could verify with the calculator. When you're multiplying or dividing, if you have the same signs, that just decides that the answer is positive. Answer. If you have one of each sign, that means that the answer is negative. This is a different set of rules than when you're adding or subtracting. Same signs, positive. One of each, negative. You have one of each here, you got a negative answer. 4 divided by 4 is 1. Okay. I need some more water. I'll be right back. If you ever feel frustrated when you're teaching or when you're learning to do something, right? Take comfort in one thing. If you feel resistance, you're learning, right? And even though nobody likes pain, right? I don't like pain, I'm allergic to pain, right? You have to admit that, at least in a physical sense, if you were, if you heard the expression, no pain, no gain, if you go to a gym, right, you lift weights, you do a bunch of push-ups, whatever, right, and it kind of hurts, right? But in the long run, what does it do? It makes you physically stronger. Well, in a similar way, when you feel some kind of confliction, when you feel conflicted mentally, because you're like, something isn't quite making sense, as long as you go through the experience, and it's the experience that matters, that resistance that you feel is making you more intelligent. Don't fight it, right? Or don't avoid it would be a better way of saying it, right? If you, anyone, right? I don't care what anyone says, right? Anyone can do this, right? Anyone can do my job. I know that for a fact, right? And if you go into the profession of teaching, you have to convince your students of that fact, right? You shouldn't have to. I mean, they should just agree with you. It would be nice, right? But the world doesn't teach them that. The world tells them that, oh, this is not for you. BS, all right? It's for them, right? This is their inheritance too, right? And in the long run, if a person does anything enough times, anyone, right, they will understand, right? But they have to have the experience, and you can't spare a person the experience. If you go to a gym and you don't lift the weights, you're not going to get stronger. Now let me show you 2 shortcuts, and then we'll finally change the subject. I'll move this. And turn off the projector again, spare the bulb. We're at 2 hours, so boys, it's going to be a long video. . rule basis. I figured that at least if it's recorded, then you have the freedom to kind of skip if you need to, especially when I go on tie breaks, right? That's not really important. Anyhow, there are two shortcuts that you might employ. These are shortcuts for special cases. When one of them is referred to as clearing fractions. That doesn't look right. And then there's another shortcut for when you're clearing decimals. Okay. What does that mean? It means you're changing the appearance of something, but not its overall value. That usually drives the kid nuts, right? Like, if there's a reason why a kid doesn't like fractions, it's because it doesn't look like what they think it really is supposed to look like, right? Clearing is sometimes referred to as eliminating. Right? And what you're doing really is you're just changing the appearance of the problem. Right? You are technically writing an equivalent.
So rather than me email you, I thought I had to email you before, it was my mistake, I do apologize. So reach out to them, and then they will enter a claim and go from there, okay, Marie? All right.
That is arguably easier. You could do anything brute force, but you might explore these two options when you're given these situations. So, in a nutshell, right? If an equation is basically an expression equal to an expression, what you're going to do strategically is you're going to multiply the entire thing times a lowest common denominator. And you're going to distribute the lowest common denominator to both sides of the equation. Because if you do that, you can change the way it looks so that there's no fractions. Right? Lowest common denominator, of course, is something that has fractions involved. In a similar way, you might have an expression set equal to an expression. And again, the whole thing is an equation, but what you do strategically is you multiply the whole thing, that is both sides, that's what makes it legal, times a power of 10. Right? You distribute that to this thing, to this thing. Right? You can get away with murder in math as long as you're consistent. Whatever you do to the left side of an equation, do to the right side. Right? Whatever you pull out of midair. Right? In this case, for clearing decimals, you're using powers of 10. In this case, for clearing fractions, you're using a lowest common denominator. Right? So, what is the power of 10? 10 to the first. Right? 10 to the second. 10 to the third. Which is really what? Times 10 times 100 times 1,000. The exponent is telling you how many zeros there are. The effect of multiplying by 10, 100, 1,000 is what? This moves a decimal point once to the right. Right? Times 100. It moves a decimal point twice to the right 1,000, it moves a decimal point thrice, 3 times, right? To the right. And if you figure out, well, what's the situation where you have the worst number of decimal places to account for, choose the power of 10 that would make it a whole number, is what you're doing. When you have fractions, it's a little bit trickier. So I'm going to put a question mark here to simulate a fraction. Yeah. And over here, sometimes 2, sometimes not. All right. You have to analyze what the denominators are. You find the least common multiple of the denominators, which is otherwise known as the lowest common denominator, LCD. This is an LCM, right? An LCM is an LCD specifically of denominators. And then you distribute that, and there's a cancellation effect. This causes a cancellation effect. Okay, that's an overview. Let me give you some examples. It's 12:30. All right. Here's an example. Oh, it's suddenly so quiet. Thank God. Yeah, I'll put this in green because it'll make it a little bit easier to manipulate. As long as it's visible. Of course not. Green is never cooperative. 2/3 x plus 1/3 is equal to 3/4. Okay. A couple of things to do. Can you do it brute force? Yes. Yes, but try this instead. What do I mean by brute force? I mean bring the 1/3 over here, convert these to the appropriate common denominator, upgrade them to equivalent fractions, right? That would work, right? But if you feel very comfortable with fractions, then go ahead and do that. But just realize that you have an option here, a shortcut. Instead, let's divvy this up into sides here and analyze what the denominators are. The denominators are 3's in this case and 4. So let us consider multiples of 3 and multiples of 4. Multiples of 4 are the products of 4 from the multiplication tables of 4. It's like counting by 4s. So 4, 8, 12, 16, 20, and it goes on into infinity. That's the one downside to this, is that sometimes it's hard to know when to stop. The multiples of 3 are 3, 6, 9, 12, 15, 18, and it goes on into infinity. And the fact of the matter is, we're looking for the least common multiple, because you wouldn't want to get the greatest one, because there is no greatest, it's infinite, right? But you can, and there may be several numbers that are the same comparing these two lists, but what's the first one? 12, right? So therefore, this is the LCM, and if we're using it for the sake of manipulating this equation, we're going to multiply this entire thing times that LCM, which is an LCD. A least common multiple is a lowest common denominator. So 12. I'm going to make that x a little bit smaller, just not to conflate it with the x here. All right. Now, what happens? You distribute 12 to each of these terms, which is why I'm drawing this little range war here, to be consistent. You can get away with this as long as you're consistent. Whatever you do here, do there. Do it to both pieces here, do it to the sole piece there. All right. If you feel, again, if you feel comfortable with fractions, you probably will just, do a shorthand, cross out whatever else, and leave what's left over. I'm going to show you the minutia because I think that makes it a little bit easier to grasp. All right. What is going on when you distribute 12 to 2/3? Well, what's going on here is that this is like 12 over 1 times 2 over 3. All right. And yeah, you could multiply the top times the top and get 24, and multiply the bottom times the bottom and get 3. And then simplify 24 divided by 3, right? Or you could do the simplifying before you multiply, which is arguably a better course of action because you're multiplying with smaller numbers then. All right? You may notice there's a relationship between this thing below the line and this thing above the line. They're both made of the factor. This has a greatest common factor, which is different from multiples. All right? The factors of 12 are things that make 12. 1, 2, 3, 4, 6, and 12. The factors of 3 are 1 and 3. Everything is made of these factors, not multiples. Multiples of 12 would be 12, 24, 36, 48, and so forth. All right? We want factors when we're simplifying. You simplify with factors. All right? They're both made of the number 3 as the GCF. So if you divide this by 3, you would get a 1 here. If you divide 12 by 3, you get a 4 here. The leftover 4 times this leftover 2 would give you what the outcome of 24 divided by 3 is, which is 8. Which means that this first term here is equivalent to 8 from all that work with an x attached to it. 8x. Okay? Next thing, if you multiply 12 by 3, 1/3, this is the minutia. You would have 12 over 1 times 1 over 3, and it would simplify in a very similar way. All right? This crosses out, becomes 1, this becomes 4. The leftover guts would be, this becomes 4. So it's plus 4. 8x plus 4 looks nothing like 2/3 x plus 1/3, but it's cool, all right? We're making an equivalent equation that will work. The fine details of distributing 12 times 3/4. It's like 12 over 1 times 3 over 4. In this case, it's going to simplify like so. 4 and 12 are both made of 4. 4 divided by itself is 1. 12 divided by 4 is 3. The leftover 3 times 3 is 9. So the equivalent equation is 9. All right? 2/3 x plus 1/3 equals 3/4 can be rewritten, this is the point of it, as an equivalent equation, 8x plus 4 equals 9. And arguably, this is a little bit easier to do because now you have a system for manipulating it. Right? And you're only dealing with whole numbers. So again, could you do this brute force? Yeah, you could move 1/3, just as you're going to move 4 here by subtraction. And there'll be a cancellation effect of 1/3. And then do the subtraction. 9 minus 4 would be 5. And then divide by 8, both sides. And you would get this as an answer. X is equal to 5/8. If you subtract 3/4 and 1/3, you'll get a fraction. If you then multiply by the reciprocal of 2/3, which is 3/2, to justify moving it, then you will eventually get to 5/8. And in theory, you could use your calculator. I don't want to dissuade you. On your calculator, at least this type, if you wanted to use this button here, ABC, this allows you to enter fractions into your calculator. So for example, if you wanted to enter 3/4, you could type it like that, all right, by pressing 3 and then this button and then 4, right, and then the operation and then the second fraction, all right. Anyhow, I don't want to talk you out of doing that, especially if you're short on time, all right, but as always, just realize there's more than one way to do something, and it's nice to have the option, right? So kind of save it in the back of your head. This is a shortcut when you get good at it, all right, that you could use to write an equivalent, and it will give you the same answer in theory. You should check it by plugging it back in, all right, but I'm not going to do that now because I know I'm going to make a 3-hour video. All right, let's do another. The other type, when you have decimals, right? If you had something that looks like this to begin with, 4x minus 0.48 equals 0.8x plus 4. All right, now this is an example of multiplying everything by a convenient power of 10, right? So let's analyze. Worst case scenario, most number of places, place values. That will decide which power of 10 we go with. 10, 100, 1,000, or so forth. All right. This is a whole number to begin with. Don't worry about it. This is evidently a decimal. How many places does it have? It goes to the 100th place, right? So therefore it has 2 place values to account for. This over here goes to the 10th place. So it's only 1 place value, right? We need to compensate for most number of places. So we're not going to choose one and then another. We're just going to go with the one that fixes both problems simultaneously. The thing that goes to the 100th place will be rectified by times 100. So we're going to go with that, right? We're going to wrap this entire thing in a parentheses. And again, you can get away with murder in math world as long as you're consistently doing the same thing. Both sides of equals. So we're going to multiply by 100 here. And this will be, it will enlarge all of the numbers consistently. So it's totally legal, right? We'll see what we get. 100 times 4 is what? It's 400 with an x attached to it. 100 times 0.48 moves the decimal place twice to the right. So this is going to be minus 48 instead. 100 times 0.8, 8/10, will move this still 2 spaces, so you have to compensate. You draw little waves maybe, so 1, 2, and therefore fill in the pocket with an 8, another 0, and this is 80x instead. 100 times 4 again is plus 400. And now, admittedly, this doesn't look anything like the thing you started with. All right? Well, it has some similarities, but it is certainly not the same looking exactly. But it is an equivalent equation. So it's perfectly legal, all right? Because you were consistently doing the same thing across the board here. All right? So how do you solve now? Make a table, maybe? All right? I personally prefer to have letters on the left side, so I'm going to scoot this 80 over here where its buddy is. And I'm going to justify doing it by considering what the sign is to start with. If it's not written, you assume it is a positive. And therefore, if you want to justify moving it over equals, you do opposite operations over equals. So, over, opposite. Minus 80, bring the letter with it. And then strategically park it underneath the thing it most closely resembles, which is its like-term friend here. There's going to purposely be a cancellation effect as a result of that. All right. And now we will do the work. 400 minus 80 will leave you with what? Well, it should leave you with, I hate to use green, but I will. 320 with an X attached to it. There's this 48 still here. This, you can put a 0 here if you like, but it's unnecessary. And there's a 400 here, which is technically a positive. So I'm going to put the positive here. And then we repeat the process. If at this stage I have decided that the x's should be exclusively on the left, then I'm going to move this 48 over here. All right? Again, if you're going over equals, you do opposite operations. The opposite of subtracting 48 is to add 48, and there's a cancellation effect by design, and then I'm going to strategically merge it together with this, plus 48 here. All right? Same signs, you add them, you get a larger 448. All right? Over here, I have this left over, 320 with an X attached to it. Now, the downside to doing this is that you end up with much larger figures than you started with. But they're whole numbers, that's the whole point. Nonetheless, I'm going to now manipulate even further. If I'm going to solve for x, I got to get x alone. So I'm going to take into consideration that two things pressed together are being multiplied, without writing the dot usually. And I'm going to move 320 from here to here, over equals, by opposite operations, which is to divide by 320 here, and to divide by 320 here. Right? There is a cancellation effect basically here, right? But it's not canceling to 0, it's simplifying really to 1, would be better to say. Anyhow, you end up with x equals something. It equals this, 448. You could use your calculator right now and it will reduce the fraction. But what I would encourage you to do is to, in the long run, memorize your multiplication tables, because you could use that as a frame of reference for simplifying. All right, it's very important. Another thing, aside from telling people foolishly that they shouldn't write anything, is that in the state of New Jersey, that people have in recent history said, "Oh, I'll make them memorize the multiplication tables." Bull crap, all right? Make your kids in 3rd grade, at least, memorize the multiplication tables, because if they do, you're building up a frame of reference. All right, what is the opposite of multiplying? Dividing. If you have no frame of reference, good luck dividing. All right, it's cutting off somebody's legs and then wondering why they're hobbled. All right, not telling them not to do that, not to memorize. All right, write what you're thinking. Memorize your multiplication tables. That is the added bonus tirade of today's lesson. You might recognize that there are relationships between this number and this number. All right, you could brute force divide 448 by 320, and that's cool if you can. Or you could try to whittle it down first, which is what I would do. The even, so you could divide by 2, or you could try dividing by 4 maybe, because there's a relationship between the 4s and the 8 and 32. I did that personally. It's not necessarily the best course of action. It's not the GCF. All right, that would have been better. The GCF is like 64. All right, but here we go. I'm going to simplify this by dividing by 4 and 4. That is a common factor. It's just not the greatest common factor. 4 goes into 4 once, goes into 4 once, goes into 8 twice. 4 goes into 32 8 times, 4 goes into 0 0 times. And you nonetheless have something that you can simplify by 4 again. 4 and 4. 4 goes into 11 roughly twice. And the difference of 11 and 8 is 3. So 32. 4 goes into 32 8 times. So you get 28 on top. 4 goes into 8 twice. And it goes into 0 0. And this is still divisible by 4. And then you have that. 28 divided by 4 is 7. And 20 divided by 4 is 5. Right? That is an improper fraction that is as reduced as possible. Right? And you might say to yourself, hey, buddy, this didn't have any fractions in it at all. So why are you giving me a fraction? Shouldn't you put it in a decimal? Yes. If you started with decimals, the expectation, the good etiquette would be give back a decimal. But before I do that, because I'm doing it by hand, I'm trying to whittle it down to an equivalent fraction, to smaller figures that are easier to divide than what I started with here, 448 over 320. It's easier to divide 7 by 5, is what I'm getting at. So if I divide what I have here, a 7 over a 5, I'm going to put some zeros in here to get rolling, literally. All right. 5 goes into 7 roughly 1 time. The difference of 7 and 5 is 2. And 5 goes into 20 exactly 4 times, which is 1.4. That means that the answer for x is 1.4. Right? Again, if you started with decimals, give back a decimal. If you started with fractions, give back a fraction. Unless it's a whole number, could be dumb luck. Anyhow, here's using a calculator. You can fit 448 in here by pressing 448 like that, and then pressing this button here, and then 320 is the denominator, and it will reduce it automatically when you hit enter. So you see 1 and 2/5, right? It's giving it to you as a mixed number. That funny symbol that looks like a U is to space it so that this is a whole and that's a fraction. Now you can, if you want to, return this into improper fraction. If you notice behind the button there are these blue symbols here. I want to say if you hit second and then hit this, it will change it to what it needs to be, an improper fraction, 7 over 5. All right. If you want to convert this to a decimal, all right, there is this button behind PRB for probability, FD. I want to say if you hit that and then you hit this, then that will tell you what the decimal equivalent is, 1.4. All right. Using a calculator is a skill, and it's something that you should teach your students, certainly. All right. But between the ages of, say, 5, and at least maybe 11 or 12, middle school, all right, being able to do things the old-fashioned way, which seems like, why am I punishing somebody? You are building up their mental strength, right? Don't try to circumvent an exercise, right? Again, don't get a gym membership and then go there and drink coffee. You don't use the equipment, you're not going to get any benefit from it, You grow mentally if you are confronted with a situation that causes a little conflict, right? A little resistance is good, right? Is the last thing, just to warn you, and then the section 6.2, which will go much quicker. There are, when it comes to your work, 3 possible outcomes. And I'm only mentioning them to you because you might unfairly, I think the word is, reproach yourself or recuse yourself right? All right. In other words, get mad at yourself for something that is really not your fault, right? Let's just say, for lack of a better phrase, there's the normal situation. And then there are these weird cases. Number 2. Okay. I really should maybe rephrase. I'm not going to double talk too much, but a normal situation is that everything goes according to plan. 16. And what do I mean by that? It means that the end result, the outcome, is that you have a letter on one side and you have a number on the opposite side. Right? That's what you're hoping will happen. That's the normal situation. Everything goes according to plan. And then there are these other weird cases, which maybe would be better to say unexpected. Unexpectedly, all right? But this is normally. You end up with this after you do all of your arithmetic flawlessly, your algebra is pristine, all right? And then you get something strange that happens, all right? And it might look like this. You end up with a number equals a different number. You know, for example, -2 equals 9. All right. Now, first of all, is that true or is that baloney? All right. Can a number equal some other number? It's not true, right? It would be false. And the way that you would signify that is not true is that you would put a no smoking cross out through that, right? So when you get a number and on the opposite side there's a different number, then you would say, no, that's nonsense. And you might automatically blame yourself. You'll go like, oh, geez, I must have done something wrong. This is the other thing that is unfortunate that you have to contend with as a teacher, all right? We people are very downtrodden, all right? And you've had bad experiences, and unfortunately you carry them with you your whole life, especially your academic life. And you go, geez, I'm stupid and I must have done something wrong. No, etch-a-sketch that thought, all right? You're not stupid. It's just that this is a weird thing that happens sometimes. Beware of it. Right? It means something, and there's a label for that. Let me continue. First, weird case number 2. Another thing that is unexpected is that you do everything right, right? But what you end up with is something that you were not expecting, which is that you end up with a number equal to itself. And you go, what? You know? Or you might get a letter, perhaps equals itself, which is not untrue, and it wouldn't be necessary to put a no smoking cross out through it. But it's still not something that you were expecting. And you might again blame yourself and go, geez, I must have done something stupid. Not necessarily, all right? And even if you made a mistake, you shouldn't call yourself stupid anyway, all right? Or other people for that matter. You should just go, well, it's just one of these 3 scenarios that is unfolding here, all right? Now, what does it mean, all right? When the normal situation occurs, all right, in a bigger picture, it means this, all right? It means that there are finite numbers of solutions. There is a finite amount of solutions. If x equals 5, it means that there's one answer. It means that it's 5. And you would put it in fancy braces and you mount it onto a plaque and you go, oh, behold the inner light that comes out of it because you're so proud of it. All right, like me. All right, don't do that. You would say there's just this one answer. It's finite. It's limited, right? And when you get to you know, quadratics, you might go, all right, well, there's two answers, -5 and +5, maybe. All right, but it's limited is the key phrase here. All right, that's the normal situation, and the operative term here is finite. Right? When you get something weird like this, it means simply there's no solution. So you would draw an empty set, right? If you wanted to be fancy, anyhow. When you do everything right, and at the end you get a dud, for lack of a better phrase, don't automatically reproach yourself and go, geez, I must have done something wrong. I'm dumb. No, it is just one of these situations that exist. There are problems that do not have a solution. So number equals something else, like -2 = 9. That's nonsense. There's no solution. Just say that. You should always double check your work, of course. Even when you get an answer correct, you should check it, because there is such a thing, you probably heard, extraneous solutions. I don't think you're going to see too many of them in this semester, but an extraneous solution is the result of manipulating an equation more than is normal. Like you multiply or divide by a letter when we haven't done that at all. But, or if you square, all right, you may end up with an extraneous solution, which is essentially a dud too. In this third scenario here, weird case number 2, you might get something that is true. It makes logical sense. A number is itself, like, you know, 7 = 7. It's like, well, yeah, apparently, you know, or slightly more nebulous would be x = x, mysterious. All right, it'd be like, yeah, I can't argue with that, you know, but, all right, it's not something you were expecting, you know. What that is suggesting, this means that there are infinite solutions. All right, and the way that you would sort of symbolize that is putting that great Gatsby R for all real solutions in a fancy braces parentheses. Okay? So, you have basically for right now, one answer, no answers, infinite answers, potentially. Right? There are names, there's labels for this, and I normally wouldn't, you know, worry about it, but it helps to give a name to something to distinguish it, especially if you're talking to another person. So let's get some names in here. All right. This situation is referred to as, instead of normal, you might call this conditional. All right, there are conditions. This letter is equal to this number, and that's pretty much it. Or some other more specific conditions than that. All right. Rather than calling this a weird case number 1, let's call this what they often refer to it as, a contradiction. It's contradicting itself. To say -2 is equal to 9 is baloney. All right, it's a contradiction. Right? Alternative to saying weird case number 2. It's weird, sure, but it would be better to say this is an identity. Okay? That's very theoretical. It's not really practical, but it does help to have a label to refer to something that means all of this specificity. Right? It's less verbose, right? And in the long run, it's more convenient. Right? So beware. The conditions of the normal situation, contradictions and identities are those weird cases. All right. finally, section 6.2 is about formulas. All right. Formulas are generally famous equations, right? But they're famous for a reason. They're famous because they are very practical. All right. Now, just to distinguish, you may have seen something like this, say in a chemistry class, for example, H2O, right? And in a physics class, you may have seen famously Einstein's equation equals mc squared, right? The reason I like to discuss these two is because they illustrate two different concepts that look similar and are easily confused. This is a subscript, whereas this is a superscript. Mathematically speaking, a superscript is an operation, right? It's a glorified form of multiplying, really, right? It would be multiplying the base times itself, in this case for square. When you see a subscript, usually what that means is that it's not an operation, it's a label, okay? It's telling you there are two hydrogen and one oxygen, and there's a one in theory that would be here for a water molecule. Right? Just make that distinction. It's very subtle, right? To have a slightly smaller font and a little bit lower or a little bit higher than normal. Right? In math world, you're more inclined to see a superscript when you're actually trying to perform an operation. Right? And it really is. Exponents is an amped up version, more precise version of multiplying. All right. Subscripts are usually part of a formula just to give you a label. Okay. Now there are basically several types of formulas that you will see in this section. Here's some useful 6.2 formulas. All right. There's the simple interest formula. And then there's volume of a rectangular solid. Specifically, because there's many volume formulas and they're different. And there's something called z-score, which comes from statistics. That would be useful at the end of the semester, really. And then there's the slope formula, or the slope-intercept. Form of the line equation. Okay, how do they look? Let me put this in blue first. All right. Simple interest is I equals, usually capital letters, but they don't have to be, capital P times R times T. The volume formula specifically for a rectangular solid is usually capital V is equal to script L, W, and H. And they sometimes put the dots implying that they're being multiplied, or they just simply press them together. And they usually script for whatever reason. The z-score is z is equal to, and they employ some Greek characters here, x minus mu is a sort of a U with flare, right here, and then sitting on top of lowercase sigma. So kind of think of, I do, I don't want to corrupt your opinion, but lowercase sigma most closely resembles an O, right? But it's an O with, like, you know, sort of a Superman curl, if you will. Right. It's got flair too, you know. The Greek characters have flair. All right, and then the slope-intercept form of the line equation is famously y is equal to mx plus b. Right. Now a little bit about each of these. I want this to be visible, so I'm going to have to use red. Simple interest is basically expressing an amount of money, I'm going to put dollars, earned or owed on a loan or an investment, depending upon where you stand. This is fake now. All right, so it's an amount of money. The individual parts involved here, let me just kind of separate these. Work like this. P stands for principal. R stands for rate. And T stands for time. There are conditions that have to be met here. Basically, and I'll use green this one time. Principal is think of it as being the original amount of money involved here. So I'm going to put this in green on purpose for the mean green. All right. Original amount of money is your principal, and it's spelled with an A, I believe. Yeah. Okay. The rate is actually a percentage that's quoted to you. The interest rate is a percent, which means that in order to use it, you're either going to have to convert it to a decimal, or you can convert it to a fraction. And sometimes it's more convenient, believe it or not, to have it as a fraction because it has zeros in it. Usually when you borrow money, it's a nice round number. So when you convert your percentage to a fraction, you have 100 as a denominator. It helps you simplify. All right. Time has to be in years. So if you ever get a trick question where they throw 18 months at you, just realize that you would have to convert 18 months to so many years, which means it's a decimal again, or a fraction. All right. Has to be years. All right. Volume is an amount of space, right? If simple interest is an amount of money, all right, then volume is an amount of space. All right, and this formula would be unique to a rectangular solid. So we're talking about something that looks like this. All right. It's just realize three numbers multiplied together. Now you do have to decide which is the length, which is the width, and which is the height, but that's what they are. This is the length, which is totally arbitrary which one it is. All right, this is a width. And this is a height, which is alternatively sometimes referred to as a depth. Okay. Depth, height, so it would be D instead of H. Anyhow, it doesn't matter which is which as long as they're in different planes. So let's say that this is the length, and this is the width, and this is the height. All right. If they have three numbers here, you multiply them together, you have a volume. All right, a Z-score is basically it's a reference number. All right, derived from this ratio. There's something called a Z-score table. All right, and towards the end of the semester, when we cover, I think it's chapter 12, I want to say, where we do basic statistics. A Z-score is a decimal number that you calculate from this ratio. Anything that has this line is a ratio. a glorified fraction, and you use it to compare to this table, all right? And the table is basically areas under a curve, all right? It represents, or it's related to, an area under a bell curve. So depending upon how much area you are taking up underneath this bell curve, a normal curve is another way of referring to it, all right? You would compare this decimal number to an established table that has areas, all right? Which in turn are referring to probabilities, which are for predicting things, all right? So for right now, don't worry too deeply about it. Just go, it's a reference number that comes from this ratio. What are these things? This is pronounced mu, and this is pronounced sigma, and they're both the lowercase incarnation of them. Now, in the actual example that you will see, x is a specific data point, or value, if you will. Mu is the average of data points. You don't really have to worry about it too much, but if you're curious, is that visible? Let's see if that helps at all, a little bit. This is average spelled out. And sigma is the standard deviation. Let me use a different color. Standard deviation is an interesting concept by itself. If you grasp the idea of average, standard deviation is its kind of its own version of an average, but it's derived differently. Average is normally a bunch of numbers added and then divided by how many numbers there are, right? Like if you had 5 tests, you would add up your tests and then divide by 5. Standard deviation is sort of an average of variation. Right? Think about each individual data point in respect of 0, right? How far are they? Some are further away, some are closer. But if you combine them in this formula for standard deviation, it's a separate formula, you could sort of calculate an average. Right? Anyhow, the problem that you have is not really about this until chapter 12, the end of the semester. What you could be doing in this section is manipulating the parts, moving them around algebraically. Then lastly is the slope-intercept form, which is probably the more immediately important thing, right? You've probably heard of this. M is the weird abbreviation that we have for slope, which is a measure of incline, right? And B is what they call the y-intercept. Don't know why that M is representative of slope, all right, but it is. YB would be. But y-intercept is where the line that you're talking about crosses the y-axis. Okay. All right, that's an overview. Now let me discuss these word problems. And I'll probably project it. Let me turn this on, and we'll go through this. Where's this stuff? this is again one of those things that you have to print if you are so inclined. If you're following along, there are basically four word problems that I'm going to walk you through. Okay. So this is blown up a bit. Okay. Fatima borrows $4,000 at simple interest rate simple interest rate of 2.9% for 3 years. So this is pretty straightforward. If they're telling you it's simple interest, that means you're going to be using this formula right away. How much will Fatima pay in interest by the end of 3 years? Now, firstly, you're going to calculate just the interest, and then as you see a little bit further down, all right, what would be the total amount that she owes or will repay by the bank? What is the total amount she will repay the bank by that time? So remember, simple interest is just the interest, right? And then you have to remember there was the original amount of money borrowed. So in theory, a person returns that as well. Right. I don't anyhow, right? That's why you'll be seeing me in debtor's prison any day now. Watch out. All right. Anyhow, 4,000. Here's how I would write this. We're going to use this number. Jeez, bringing your family over and over again. There is no worse marker out of the package than green. I don't know why, right? But it's always lousy. When you use 3, it's a different green. It does the exact same problem. And here's that one. Oh man, one is worse than the next. All right. We're basically going to multiply these 3 numbers, but in their peculiar style of writing. So I'm going to have to just stick with something that is the most visible, which is black. All right. So the principal is the original amount of money. I just know from experience, write 4,000 as a fraction. Right? How do you do that without changing its value? Stick a 1 under it. All right. Now it's an improper fraction, granted, but you'll see the convenience of this in a moment. You could just enter these figures into your calculator, but compensate with the decimal. This here, right? 2.9%. If it says it's a percent, that means that it's over 100 already, right? So that means that the figure that is adjacent here is times 2.9 over 100. And you see that even though it isn't technically a fraction, it would be more appropriate to call it a ratio, all right? It still simulates a fraction. And then this last thing is 3. So 3 years. So I'm going to just put this again, disguised as a fraction. I'll just stick it over 1. All right. The benefit of writing these 3 things that you're going to multiply anyhow, as such, is that you can do some kind of simplifying here and spare yourself a little bit of trouble. Right? Here's a shortcut, right? That is especially if you're doing this by hand, right? 2 zeros here underneath the line, 2 zeros here above the line. That's like dividing by 100 without really thinking. All right? And that means that you have 1 times 1 times 1 as a denominator, which is superfluous. You don't have to write it anymore. You could put it here, it's certainly not wrong if you do. That's not wrong, all right? But it is unnecessary, all right? It's simplified. Now what are you left with on the top here? 40 times 2.9 times 3. And remember, there's a commutative property of multiplication, which says that if you're just multiplying, and that's really all you're doing now, you could do it in any peculiar order you like. So I'm just going to write it like it would be interesting to do it as. Again, this is if you're doing it by hand, strategically. All right? I'm putting this 3 next to this 40 only for the reason that I want to emphasize that in my own mind I'm doing that first. What's 4 times 3? 12, right? What's 12 with a 0 attached to it? 120. right? That means that it's really now 120 times 2.9. Now at this point, admittedly, you're kind of stuck with it. You could sort of, maybe finagle something, but it's a lot easier at this point to just simply type 120 times 2.9, right? And if you had a better number than that, like let's just say hypothetically if it was 3 instead of 2.9, right, you probably wouldn't need a calculator at all, right? Anyhow, the end result from multiplying is this. Let's see. You should get 348. That's just the interest that a person would owe from borrowing money. Okay. All right, anyhow. Now, logically, if that's the way it works out in terms of the interest, how would we decide, that's part A, how would we answer the second portion of this, which is, well, what is the total then? There is a formula which looks like this. A, capital A, equals P plus I. But you don't need the formula. You probably could just infer it logically yourself. If you know that there's a total, that's probably going to add or subtract something, right? In this case, we're talking about money owed. It's going to add up for the person that's owed the money. A stands for value of an account. Account. We could say amount owed. Total. Same difference. P is still principal and I is interest. So if the original amount of money was $4,000, essentially you would infer what's $4,000 plus 348. Right? $4,348. Okay? Okay. Next problem is a volume problem. Take a look at this. I tried to leave a little bit of space to work. Number 2, use the formula for the volume of a rectangular solid, which is this, V equals LWH, to calculate the width specifically, right, of a box of ice cream given these known dimensions. All right, 7 inches long, so in place of L, you're going to put 7. 3.5 inches tall, so that might appropriately go in place of height, 3.5, and 122.5 inches cubed in volume. So you're not going to put it here, you're going to put the 122.5 here. Right? And notice what ends up happening. The variable is, this is an algebra problem because we have to solve for the letter here, all right, rather than just do arithmetic of multiplication and it spits out the answer automatically. So, if you're just looking at the figures for a moment, and really you should analyze what the units are too, but you can get away with it in this case, not doing that. If these things are all being multiplied together, right, if you're going to solve for W, that means you got to get W alone. How do you justify doing that? You move stuff over the equals, right? Now, usually it's just one thing that you're doing, not two things simultaneously, but the logic still holds true. So you can do it in 2 steps or you can do it in 1 step. Here's what I would do. I would say, all right, everything is being multiplied here, and I want to get this alone. So I'm going to freeze that in place. but I'm going to move the 3.5 and the 7 to the opposite side. I know it's written backwards, but it still works. What is the opposite of multiplying by 7? Dividing by 7. So I'm just going to stick a 7 under a line here. And that means that this will be divided by 7. Simultaneously, I'm going to try to move 3.5. What is the opposite of multiplying by 3.5? Dividing by 3.5. So I'm going to divide by 3.5 here as well. I'm going to put a dot here just to unify them. And then a dot here just to unify them. And remind you, I have done this consistently to both sides. And that as long as everything is a factor, and that's what those dots are indicating, you could cross them out. 7 divided by itself is 1. 3.5 divided by itself is 1. And this line means division. When you get over here, you can enter this into your calculator if you're very, very careful. You would have to employ parentheses probably. What you might do is just simply simplify this first down to one figure. And then when you type into your calculator, just do one thing from the top and whatever that works out to be on the bottom, right? So what is actually 3.5 times 7, 2? 21 plus 2 is 23. It would be dividing 122.5 by 23.1. Right? And you should get 5.30 repeating, is that right? Nah, I must have miffed it. All right. 35, ding dong, that's why. Sorry. 5 times 7, this is why sloppy handwriting is not good. 7 times 5 is 35, carry the 3. 21 plus 3 is 24, right? 24.5. Alright, so 122.5 divided by 24.5, you get a nice whole number, should be 5. See, 122.5 divided by 24.5, yeah. Okay. So, the width dimension is equal to 5. Now, insofar as the units are concerned, if you're worried about it, in a physics class, it would definitely be important, right? This is a volume, so it is in inches cubed because it's representative of 3 dimensions, right? Width, height, and length. Anyhow, these are just 2 of those dimensions when you multiply it. The abbreviation basically for inches times inches would be inches squared, right? Insofar as the exponents are concerned, when you're dividing like exponents, like bases, inches and inches in this case, you would subtract these technically, all right? And then you would end up with what it's supposed to be, which is inches to the first degree. Okay, so it's 5 inches literally, specifically. Okay, get the digits first, and then you can always rationalize how the units will work out via cancellation later, right? Now take a look at 3 here. All right, here's that z-score formula. It's a little bit more complicated, this particular example, but don't be deterred. All right, it's just that this is a thrown in extra feature here. All right. All things are given to you, all right? Instead of calling this x bar is another way of saying average, actually. But this is 120 right here, all right? Mu is 100. Sigma is 16, so it's down here. And n, a number I suppose, is the square root of 4. Now, notice that all of the features are filled in on one side of the formula, which means that you're going to just simplify this, in which case you would follow the order of operations. All right. This is a situation where you have something that is, technically speaking, a rational expression, And if you have a rational expression, you have an obvious top and an obvious bottom, right? What I would suggest you do is simplify the top first, simplify the bottom second, and then divide the top by the bottom if it's possible last. It's kind of, it would seem to be bending the rules a little bit. It's not, because in the bottom or the top in a more complicated problem, there might have been multiplication or division. There isn't in this case. Well, there is here actually. So you will do that appropriately, right? But as a technicality, right, you can't divide one thing on the bottom by two things simultaneously. You would have to logically combine the bottom pieces. And the only way you can is by straightening out 16 and square root of 4. Anyhow, let's just deal with the top. What is 120 minus 100? That would be a 20 above the line. This is 16 sitting on top of the square root of 4. In the same way that exponents is an amped up version of multiplication, square roots and things like that, like cube root or what have you, are a more sophisticated, more precise form of division. It's division in theory when the quotient and the divisor would be the same figure, right? You don't bother to write either of them, actually. This is a square root. What number times itself makes 4? It would be 2, right? This is now 16 divided by 2. As another technicality, you might be wondering, well, why are you taking that square root there? All right. Well, I would have to, according to the order of operations, it's more important than regular division here. All right. But it also would be difficult to divide by a radical. All right. What is 16 divided by 2? This is 8. So that means that you really have z is equal to 20 over 8, which, again, it's a reference number that you get from straightening this figure here, this ratio. It's a decimal. So how many 8s can you squeeze into 20, roughly? I'll use a different color because I'm scribbling a lot. 8 goes into 20 roughly twice, which is 16. The difference of 20 and 16 is 4. 8 goes into 40 exactly 5 times. So when all is said and done, you get this decimal number 2.5. All right. Again, in chapter 12, you will see this is a reference number. All right. And you look at a table and you go, oh, it's 2.5. All right. And that correlates to an area. The last thing for the day here. I feel like I said that 10 times today. Sorry if I seem like I'm lying, I'm not. Last is a relative term. At least in the context I'm using it. Slope-intercept form of a line. Okay, again, in the long run, more immediately, this is going to be important to us, right, before anything else. M is a slope, which again controls incline of your line, how it's pitched, basically. And this is a y-intercept, which is the point where the line crosses the y-axis. So if you had an axis of x comma y, and you ended up with some kind of a line that crosses it, that location would be the b value, right? The y portion of the coordinates. All right, now in this case, the point of this exercise is not really to graph anything. It's just to get comfortable with manipulating something algebraically. The problem, like number 2, is more similar to this. Y is equal to mx plus b. So if you are going to solve for m, that means that you're basically going to move everything away from this. You're going to freeze that in place, and this has got to go over equals at some point, and this has got to go over equals at some point, which means that you're going to employ opposite operations. Generally, you do the addition and subtraction portion of the opposite operations first. That is, when you're moving over equals, as you would in this case, you would subtract by b, and you would subtract b to be consistent. All right? Now, one thing you have to forgive yourself and the situation. Do you know what b is? No, you don't. But you still, legally speaking, can manipulate this way. Something divided by, something minus itself, even if it's mysterious, cancels via opposite operations. What you're left with here, you can't do anything with, but simply, rather than write vertically, write out more or less horizontally. So you would have y minus b on this side. What's left over here is m and an x attached to it. If, again, you're solving for m, you're trying to get m alone on one side, which means you have to move the m. How would you justify doing that? Well, if it's multiplied, I divide to both sides m. X, one letter. So used to using x's. So divide by x here, divide by x here. X's, I don't know what they are, they cancel. So what is m? Written in a more normal orientation, I suppose. The usual orientation, that is with the letter on the left. This is what you would end up with. If you're rearranging the parts algebraically, you're just moving things around via opposite operations. If you're trying to get m solved for, then this is the way it would work out. Y minus b divided by x, the whole thing with an x under it. Okay? That's 3.5 hours. I hope that was thorough, though. So, what to do for homework, right? If you're keeping pace with the schedule, right, what you should do is do section 6.1 and 6.2 in my lab. Right, and if you go up to that point, then you're right on target. Okay, please work on that. And if you're a little behind, try to catch up. Right, you have until the end of the month at least, March 1st, evening of March 1st. All right, but don't get too far behind because you know it kind of gets away from you. Okay, thank you for sticking with me for 3.5 hours. I will talk to you again on Wednesday.